As Giulio asked in the starting of the conference to try to address the students, there are not so many students, maybe, but I still will try and so make questions, okay? And this is a computational talk, okay? So I guess no one is working on what I'm doing. What I may ask you is to think whether some of the problems you are dealing with could profit from something related to the methods I will talk, okay? So I will be based on two pillars that I think, based on what we heard today and mainly yesterday, should be raise no discussion. So first, that the existence of deterministic chaos motivates statistics or probabilistic description of dynamical systems, right? And the second is that numerics or numerical simulations are essential to understand dynamical systems, both to motivate the theory and also to address systems that cannot be dealt analytically, right? So, but if we agree on this, and I think this was the basis of many of previous talks, I can formulate the problem I will address here, and I hope it will not be too restrictive. So I'm interested here in a dynamics happening in a potentially high-dimensional phase space, X. This dynamics is evolved over time, and we will focus on an observable quantity, and this is low dimensions. For simplicity, 1 dimension, and this is dependent on the initial condition and at a given time. But as usual, we are not interested in a single trajectory, but on an ensemble of trajectories, right? So sampled according to some measure. Could be the invariant measure of the dynamical systems, could be a uniform measure. So if we do so, we will not have a single observable, but a distribution of observables. One for each initial condition if you we would be sampling according to the measure here, right? So the problem I'm interested is how is to compute trajectories that are on the tail of this distribution, right? So the initial conditions here that lead to the observable that is in the tail, okay? And why is this a computational difficult problem? Because let's say we want to find these trajectories, or we want to estimate the magnitude of the tail, the probability of finding a trajectory with an observable larger than a given threshold, right? So the area of this curve. So we would be summing over all trajectories, right? So and checking this, the delta function is just saying, is the trajectory here or not, right? So that will be what I believe most of the simulations that were done so far here is doing. They will sample the trajectories here uniformly, you compute these, and then you do this sum. But if this, what will be the computational cost for that? Well, the computational cost will be the number of samples you need to find a certain number of trajectories in the tail, right? So if you want to estimate this area, you need a certain number of trajectories there to have some confidence about your estimation. So let's say the number, this number that you believe you need to have a given uncertainty in your estimation. This is m star. So the computational cost will be measured essentially by how many trajectories m here I have to sample to find m star trajectories. And of course, this will be just m star divided by the probability of finding this trajectory. So the computational cost, if this distribution is falling exponentially, it is, as it often does, the cost will grow exponentially with the threshold. So it is exponentially hard to solve this problem. Okay, and so when this is the problem I will try to see, how can we, for instance, change the computational cost to be able to sample rare trajectories more efficiently than exponentially? Yes. Your choice of the volume of the in the phase space is fixed. You can then sample as many trajectories as you want. The volume is fixed, but m. Yes. Okay, and so there are two spaces: the phase space and the observable space. I drew them before the talk here because we'll be coming back to this. Okay, so I hope you already see some examples of problems that can be mapped at, but I'll give some motivations for this problem, for further motivation. So why to study rare trajectories? Okay, so since most of this work was done in Dresden, where I met probably most of the people I know here, I thought it would be a good example to illustrate the importance of rare trajectories because they generate extreme events, right? So this is the river Elbe, and which usually runs here, and in 2002 it had a flood. This is the type of extreme events in Dresden, and if we measure the precipitation as a function of time, this corresponds to the rain of 2 monthly averages in a single day, and this is the cause of flood here, right? So we could imagine that we have a weather model. This will be our high-dimensional phase space, and that we will know with some certainty, and we would like to know what is the probability to have a precipitation as large as this one, or larger than 50 millimeters in a day. So the precipitation will be the observable, okay? And the dynamical systems will be our weather model that we are trying to simulate, and the ensemble of initial conditions are initial conditions compatible with what we know today, right? So the true extreme event here is that this is the best beer garden in town, and so it's closed because it's flooded. So it's a disaster, right? Yeah. Maybe some Brazilians don't know, but August is one of the few months you can go to the beer garden. So it's a true disaster because the rest of the year you cannot sit outside. Okay, so it's a serious problem. So another motivation to study rare trajectories is because often to characterize the dynamical systems, we are interested in these trajectories. For instance, in problems such as chaotic scattering. So I'm thinking here that a point particle is flying into to these 3 hard disks and colliding with these disks elastically, right? So somehow, something like that. Okay, this is a very long-lived trajectory. It's a very rare trajectory. It bounces many times here before it leaves. And these long-living trajectories are essential to characterize these systems. If you want to define Lyapunov exponents, or if you want to compute escape rate, or if you want to compute fractal dimensions of these systems, they are defined in the invariant sets, so the never escaping orbits and its manifolds. And there are also analogies to many physical applications in fluids or in chemical reactions. This could be a reactant zone in a microcanonic view. So finding these rare trajectories are important to characterize this system. And how do these rare trajectories look like in this toy model? They are fractally distributed, right? So if I plot the time it takes to exit as a function of the initial position x here, we see that this is distributed in a Cantor set-like way, right? So, or more formally, there is a countable infinite number of points in x here where this function diverges. Okay, so it has some fractal structure. If we magnify this region, we see against the same picture, and the volume, the number of particles that has not escaped until t decays exponentially, with an exponent that is kappa here, the escape rate of the system. And this happens also in higher dimensions, right? So, and that's where things start to get fun. For instance, this is a series of 4 coupled Henon maps. I'm plotting here only 2 of the coordinates, and we see that these are phase space coordinates, right? So in the phase space, and the vertical axis is now our observable. So t here is the escape time, is what was e before, right? So it's how long it takes to escape. And we see that we have again this singular fractal-like function, okay? Which we need to be able to track the peaks if we want to characterize this system. Another example, the famous standard map. If you are interested in computing the finite time Lyapunov exponent, again, so this is a fully chaotic regime. So if you plot the phase space variables, theta and p, and the observable here I'm plotting is t times the finite time Lyapunov. I believe t is relatively small here. So here are the distributions for different t's. So we see again our phase space has this very complicated fractal-like structure. Okay, so this is my motivation for this. Is there anyone that is not motivated to learn how to compute more efficiently rare trajectories? Is there any question? Any? Is it clear? So the type of problem. Can you imagine a problem where you, in your work, that this would appear or that you studied? Maybe? Yes? It's a numerical work, so it will be, yes, we have here a dynamics, and the dynamics maybe is defined by some, so we have the position at some time t will be is a function of the position at time 0. So this push forward function here is usually hard to compute analytically. I'm considering that you have numerical methods to compute this for any trajectory, right? Could be integrating a continuous time system or iterating a map. Okay? Okay, so yes, for this problem, it's also important the tails of these distributions, right? So I'm interested in the tails, so the initial conditions which are more or less chaotic in a finite time t. Okay, what can we do computationally? What are the ideas? This is also not new in my work. So how can we compute this? So the basic idea is that we will not, we are still interested, this is important, so we are still interested in this distribution. We are interested in the physical problem of sampling according to the red initial conditions, but we will not do that numerically because that is expensive. So I will choose another distribution in my phase space such that I will be sampling the energy, the observable here, in a skewed way, and hopefully reduce my computational cost from exponential, for instance, to polynomial. That will be our holy grail, right? So, and of course, we are still interested in computing the right probability, so we will be still summing our observations in the purple sample space, but then we will be correcting. We will be correcting by what is the bias probability of sampling this. So I'm introducing a bias towards the purple distribution, and what is the original probability. So I'm interested in correcting in the original problem. I'm not shifting the problem. I'm just sampling through the purple initial conditions to be more efficient. But I still want to answer the original question. For instance, what is the area, the blue area? Okay? And how we do that, of course, this is the idea of Monte Carlo methods, right? So that go back to, as referred before, to Ulam, to Metropolis, and Hastings. And just as a motivation, a general motivation, if you look at the frequency of usage of these terms in books, right? So in general books, we see the rise of Monte Carlo in the late 40s, and it's very popular in different types of computation, in chemistry, in physics, molecular dynamics, protein configurations. But we see also a huge rise of these other keywords, MCMC, Markov chain, Monte Carlo. This is what computer scientists call Monte Carlo, right? And from the 91 on, this had a huge impact of what we know now as machine learning, data science. And this is essentially the rise of Bayesian statistics and applications to data science heavily relies on Markov chain Monte Carlo method. So these ideas that started in physics have now an impact in areas that are much broader and have much more impact than physics or than statistical physics. And hopefully we can contribute there too. Okay, so that is a general message. But what is the idea of Markov chain Monte Carlo? So I have an initial condition in my phase space, and I will propose a different one, a purple initial condition, according to a distribution. And then I will accept or reject this proposal. And the Metropolis Hastings choice of acceptance rejection tells me that I should accept a move from x to x prime according to this probability, where g x given x prime is the probability of going from x to x prime. So gx prime x is therefore the reverse probability. And pi is not the number pi. Here is a probability, the bias probability. Right? So it's the bias I choose to give to a point in X or X prime. Okay, and what Metropolis Hastings showed is that with this choice, if the proposal here is ergodic, if any point X is, you can visit this in the Markov chain, this choice guarantees detailed balance, and therefore the Markov chain, the equilibrium distribution of the Markov chain will be pi. Okay, this is a fact. Provided the proposal, it is possible to reach any point X in the original phase space. Okay, so what are the usual choices of pi? In statistical physics, we are using in what I'm calling here a canonical ensemble, right? So this will be e to the beta energy, right? So beta will be our inverse temperature in statistical physics. Sometimes this is not good enough because you can get trapped. And I will be also using what I'm calling here a flat histogram distribution. And this is a very smart idea. I think it goes back to Berg in the 90s, which is I choose my the probability as the inverse of P. So the choice, and it will be clear in a minute what this means. Okay, so let me give you one example. For instance, what is this flat histogram? Suppose this is my red distribution. The distribution I'm interested in is decaying exponentially, and with this exponentially high cost, as mentioned before. So the flat distribution would mean that I define a minimum and a maximum observable, and I say that the probability of visiting any of these points is the same. So this is good for any point. Right? So I want this. I want to fix that. Okay? Sorry? I modify the tails. That would be ideal, right? So if I could do that, if I could sample from this distribution, it would be great. How do we sample? The Markov chain way of sampling, or most Markov and Metropolis Hastings algorithms, do that by doing local moves, right? So if by chance, suppose by chance I found a very rare state, I want to use this information so that the next state I propose, X prime, has a similar observable, a similar energy. That is the idea. So I will be making local steps here. Right? So if I found a rare trajectory, the next one I propose should be close to that. Okay? And if I do that, ideally I could perform a random walk here. This is a random walk in a finite domain from Emin to Emax. So the efficiency, the number of trials here, I have to be careful because my samples are now correlated. They are not independent. So to guarantee that I have independent samples, I will wait until my random walk here will tunnel from the minimum to the maximum. This guarantees that I lose correlations. Okay, so the number of trials here is the number of simulations I need to find an independent sample in any of the regions, because this is flat now. So that's why I find this E squared ideal cost, because this is the time it takes to diffuse in a bounded domain of size Emax. Okay, it's square root of t, so I get Emax squared here. Okay, so in practice, I will be building a proposal. The proposal is done in X, because that's the only thing I control. I control in the phase space here, right? My proposal is in X, but the proposal in X has to guarantee that, as we will see later, that in the observable it is local. I will accept, reject the metropolis according to this probability. So that is what I mentioned before. I apologize for the notation. Sometimes I call the distributions Rho, sometimes capital P. But so usually you don't know this distribution Rho. If you don't know, this is where this very powerful method developed in statistical physics, the Wang-Landau method, comes into play, and this is a way of converging. It's an adaptive method. It's a non-Markovian adaptive method that you essentially adapt your distribution to converge to that. I will not enter into that, but there are sophisticated methods that allow you to do flat histogram simulations even if you don't know the initial. Okay? Exactly. That's exactly the point. Let's pause and think now away from the physics problems, right? So what we are, let's look only from a computational point of view. what is the challenge here? Because we know that Monte Carlo suffers, and it's also good for dealing with rough landscapes, right? So landscapes that have multiple local minima, local maxima. And fractality in this context, right? So we could, in a typical computational method to find maxima or minima of function would be a gradient descent, right? So you start in a point, you look the direction where it's steepest, and you walk in that direction. But then you get trapped in a local maxima or minima if there are many of these. And here, it's an extreme case. There is a fractally distributed number of singularities, right? So that's an extremely difficult computational problem. And that is exactly when the flat histogram simulation is indeed very powerful to avoid this, right? So to avoid, because you will be walking in this direction up and down, up and down. So this helps you getting avoid. Sorry? Yeah, that's all I can do, because I need to try to correlate my trajectories to walk in this direction, right? So because if I don't correlate, I go to the middle of the distribution. Okay, we'll come back to that. What is our contribution? What is the contribution I'm trying to present here? Is to how to construct this proposal for chaotic dynamical systems. Okay, so that is our contribution, because precisely, suppose we have different x here, and we are computing the observables. These are different initial conditions, how they evolve in time, projected to one variable, or this could be even the observable. So suppose we found a rare trajectory. We are happy with that. But if we don't correlate, if we just choose another one randomly, it will go again into the middle of the distribution, right? So it is way more likely to find a trajectory here than to find this one. So if I found a rare one, I have to use this to find another one. Okay? And so what is the idea? I want to correlate my next trajectory based on the previous one. And the basic idea is that I want to find the proposed trajectory that is similar to this one until a given time, which I call T star, a correlation time. From there on, they can diverge, because I still want to move, right? So I want to be close, but not identical. I still want to move. So that is, I will correlate until a given time, and then allow it to move so that I will be moving here, but moving locally. That's the whole idea. How do we compute this correlation time? I will come later about to how we are able to do that. But first, our contribution is to argue how to compute this correlation time, and I want to give you an idea of the argument. Ideally, we would like to do that by imposing that the acceptance, so expected acceptance given all x. So every time I propose, I accept or reject. If I reject all the time, this is extremely inefficient. I lose moves. Or in other words, my samples become extremely correlated. So to lose correlation, I have to accept the moves. Otherwise, I'm not sampling anything new. So I want the acceptance to be a constant, or you could think it would be a 1, but this is not so important. But but this is hard. We're unable to continue with this. So the simplifying assumption we use is that the proposal from x to x prime and from x to x prime from x to x prime and from x prime to x, they are of the same order of magnitude. So if we have these two terms here of the same order of magnitude, what we can try to impose that the expectation value of these terms, the remaining terms, so the biased distribution I choose, should be almost a constant. And this we can proceed. So we will be computing this T star, imposing that the expectation of the bias probability between x and x prime is almost a constant, which is essentially just guaranteeing that you are making local moves here. Making local moves is enough to guarantee that. Okay, but so in other words, the local moves that I have been arguing before are essentially closely related to the guarantee that the acceptance is not going to 0, because otherwise your acceptance goes to 0 and you ruin all purpose, right? So, for instance, the things we are able to calculate, I will not enter in the details, but depending whether I want to get a canonical or the flat histogram distribution, depending on the problem, computing the escape time or the finite time Lyapunov exponent, I get different expressions for this T star. So I know what my T star will be. For instance, for the canonical distribution, this T star will depend on the escape time I'm interested, or of the trajectory X. This is the trajectory where I am, the acceptance I'm choosing, the escape rate of the system, and beta is the inverse temperature that I'm choosing here. Okay, for the finite time Lyapunov exponent is something similar. Okay, I know how to compute, that's what we did, how to compute T star. Not yet, it will come now, in a minute. Not in the choice of how long. Yes, so maybe this will answer, okay? So how do we correlate the trajectories in practice for a time T star? Okay, there are two ways of correlating. So the first one is, I think what you had in mind, is proposing in a closed neighborhood. Right, so because they are initially close, but if the trajectories diverge exponentially with an lambda L here is the largest Lyapunov exponent or the largest finite time Lyapunov exponent in the point X. So if they will diverge with this rate, I have to choose a time that is a distance that is precisely capital delta here is a constant, but this is E minus this exponent times T star. So they have to be very, very close to each other so that to remain a T star time together. In the stable manifold of this, yes. So my claim here is that we will be proposing with a n-dimensional Gaussian distribution with a width given by this. Okay, so yes, but remember, you have to have you have to be able to go from X to X prime and from X prime to X, because these terms are appearing here. We can the stable manifold of the trajectory X. That's what you are saying. But I want to move. So maybe there is an insight there. But I'm saying that for the Metropolis Hastings to work, my proposal has to be ergodic. So I have to be able to go to any other point. And this Gaussian distribution ensures that, because there is a non-zero probability to go anywhere. And I have to be able to go from X to X prime and X prime to X for all X and X prime. So, and this is then computable here. And we will need to do the same with that. But maybe it is possible to use this insight. There is another way of correlating, okay? It's just, I want to emphasize that there is another way of correlating the trajectories, which is not only making the local. And this is the shift proposal. I can just walk along the trajectory, okay? So these are the two ways I know, and we will be always using a combination of the two. And in the shift trajectory, we are using, indeed, the T star minus the T naught, because this is the amount of time that the trajectories will be identical. It's the difference between what I correlate and the total time of my observation. Okay, so I will be using a combination of these two ideas, using the same T star here and here to perform the steps. And that is the idea. That's the essential idea, how to construct a proposal that makes an efficient sampling of the T of the distributions. So the next is to go through 3 case studies. Okay, but is there any question about the basic ideas? Okay, so that is my computational toolbox, and I want now to convince you that some toy models, some basic systems we study in nonlinear dynamics, we can do this successfully. Let me start with this more recent work. This was PhD student Diego Tapias, that was in Mexico. It's now in Göttingen. the Max Planck in Göttingen that visited me in Sydney for 6 months, and we were able to perform this. So the idea is to investigate diffusion, right? So we start a bunch of trajectories localized in space. You observe that after sometimes they move. We are interested in the distribution of the particles at a distance r of the origin, and if the process is described by a diffusion equation, is a Brownell motion, we would expect that the distribution of the particles at time t will be given by Rayleigh distribution. This is the so-called Rayleigh distribution, where d is the diffusion coefficient, t is the time we are observing, and r is this distance. Okay, and this is what we are interested now, is computing trajectories that go, that are in the tail of the distribution, trajectories that diffuse very quickly. Okay, but we are interested, we are assuming that the dynamics here is not stochastic. There is a deterministic chaotic dynamics. So, for instance, what we will be doing in one of the cases is considering the Lorentz gas, right? So, the finite horizons Lorentz gas. This is a hard spheres, and the trajectory bounce collides elastically here, and by doing that, it moves, right? So, what happens if we do that for many particles? Most of them get close to our unit cell, right? So it's diffusion. But some of them, you see, they are moving almost ballistically. Right, so, and how do we find these trajectories? These are precisely the rare trajectories that have a very large displacement at that time, and we found these ones through our method. But look, we are not only finding it, we are sampling it, right? So we are finding them randomly. We have the same probability to find any of them, and we know what to remap the problem to the original, so to reweight and know what is the probability of finding it under a random search. So it's not about going, and finding a ballistic trajectory, a ballistic orbit. It's not just finding one of these orbits or the largest orbit. It's being able to do in a proper metropolis Hastings setting so that we sample them according to a probability, and we know what is this probability. Okay. Another example that we can do analytical calculation is this piecewise map. I believe this one was introduced by Klages and Dorfman in the 90s. So the position at t plus 1 is a discrete time system. Depending on x of t is given by this piecewise function. So if I start a trajectory here, it will be bouncing like that. It will be moving like that. So and if we consider the spatially extended version of it, it can go to plus or minus infinity. So this is, the phase space is one-dimensional now. And most trajectories, again, remain close to the origin, but there are rare trajectories that are moving ballistically. This will be related to periodic orbits here. Okay, so but so the idea, again, in this case, will be to bias the distribution. In this case, we are doing a canonical choice, and we know how to choose my parameter beta if I'm interested in a threshold r star, right? So I'm biased, my bias distribution will be picked around r star, so that I can have a good sample to the right and to the left of the tail. So this is the distribution we will be choosing. So, I will be measuring the cost as a number of samples to do that. And if I would be able to, I can compute analytically the cost for the red and for the blue trajectory, assuming I can sample ideally from this distribution, right? So I'm ignoring now the Markov chain process, just saying, assume I am able to draw IID samples from the red distribution. That would be the best case scenario. And then in this case, we can compute analytically for the problem of r star equals t over 2. So my boundary here grows with t, just to be able to have a single scale here, a single large limit, and beta is then in this case equals beta star, is a fixed value. So in this case, we know that the computational cost of just doing direct sampling, just searching randomly as we would do, right? So sampling uniformly would be this one, while the cost, if we are able to do the best possible Markov chain, would be this one, would be a huge improvement. And this, what we are also able to compute is what will be the Metropolis Hastings method without our smart proposal, okay? Just a Metropolis Hastings where we also choose randomly initial conditions. And this is, of course, not helping because you correlate trajectories, but you are not improving the sample. So again, we do our MCMC with our shift and neighborhood search. We perform our calculation for T star. In this case, for the canonical choice, we have a function that of T star that depends now on T. That was your question, Arkady. So this T star now for this depends on T. T is the time I'm measuring now the position of my particle, diffusive particle. And it depends on the diffusion coefficient, which we can estimate roughly. And beta is the inverse temperature here, and A is our acceptance. No, it's between 0 and 1. It's between 0 and 1, yeah. Yes. Right. But this will be larger than 1, 2. So I think there's a double negative here, no? Yes, I think this is a misleading way, but this T star should be smaller than T, right? Yes. Okay, so this is for this system where we can compute analytically, since the T I'm choosing here is finite, is probably around 8 or 10, it's just for illustrative purpose. My distribution is not this Rayleigh distribution, or not, it's not a Gaussian distribution of particles, but it is this stepwise distribution because of the piecewise linear case here, right? So, and my bias distribution, so this will be the Gaussian or Rayleigh, maybe it will be the right word here, and this is the biased Gaussian, and this is the biased true distribution, right? So the purple is the true distribution, and the red is the biased true distribution. And this is what we obtain. So now the red and the blue are simulations through our method. So what I'm emphasizing here is that our method is not drawing from the Gaussian approximation, from the Rayleigh approximation. It is drawing from the true distribution. Right, so we are drawing from a true distribution. So we are able to capture even this piecewise linear property, right? So in particular, so if our intention was to sample this distribution originally, we are able to do that, right? So, and this is now for the Lorentz gas example. So this is now the Rayleigh distribution is a better approximation, but still we see, since this is finite time, I apologize, so the time should be around 20. The true distribution we don't know for finite time. The approximation, the Rayleigh approximation here is as a dashed line. So in blue is what we would obtain naively if I just start random initial conditions. And in green, with the same computational cost, is what we obtain with our bias sample, right? So we are able to go here 4 orders of magnitude down in probability, right? So, but notice that we capture, so we are of course not as good as the random one for the core of the distribution because, well, we can discuss this later, but what is important is that both our Metropolis Hastings and the direct simulation agree even on the fluctuations. Right, so because it is not, we are not approximating the distribution, we are just biasing it, so we are able to remap our bias. So this is our bias sample, and we remap the bias sample to the original distribution, so we have an excellent agreement between the two. And in terms of so the trajectories, these rare trajectories, these rare blue trajectories are trajectories in this tail here, right? So we are sampling from this tail, while the red ones are trajectories around the maximum of the density of the statistical mechanics jargon, right? So the maximum of this distribution. Okay, so as a computational cost, now we had these two ideal cases, and the direct sampling is following our analytical result, and our Metropolis Hastings is of course worse than an ideal computation we did, but still it seems to be parallel. It seems to be just a shift. So we are improving a scaling that is like that to a scaling that is like that. And that is what we were aiming for. Okay? So the second example, the second case study is the case of chaotic scattering. So this was I showed you before. This was the coupled Henon maps and the escape time. So here again, we can think in terms of what am I doing. So suppose I find a distribution here. What is the neighborhood I should search if I want to climb? And so this is too big of a neighborhood. So I will be most likely always going down. So I have to scale my search space appropriately. And if I'm able to climb up, I should again scale it and narrow it. So the higher I am, the smaller must be this region, right? So, and this is what our theory is showing how to do that, computing the T star and scaling by the Lyapunov exponent, right? So indeed, here we did a simulation in that system showing that so this is the acceptance rate as a function of the escape time, which is my observable. And if I choose the T equals T star, I find that it remains a constant for arbitrarily large escape times. Well, if I choose something that is slightly larger or slightly smaller, it goes either to 0 or 1. 1 here could seem to be good. You are always accepting, but the convention is that if you propose if the observable is the same for x and x prime, you always accept. So your acceptance here is because your search region is too narrow. You are essentially not moving. You are proposing a trajectory that is identical to what you have. You accept by convention because this increases the mixing of the Markov chain, but this is not helping. Okay, so this one here is not helping. And this is what our theory expected, and this is what we predict, okay? If we don't know the maximum Lyapunov time, we can use the local, or we can make an adaptive procedure. So this is an example. So this will be the escape type distribution for the Henon, the coupled Henon. This is what you obtain in black for the just uniform sampling, and with our method we obtain the red one. It agrees again in the fluctuations, but with the same computational time here we can get 20 orders of magnitude more, right? So just as an illustration. And these will be the computational cost. Uniform sampling is exponential. The ideal case will be t squared, where we obtain for Henon something that looks polynomially. There is a larger exponent, which is some sort of critical slowing down, but it is polynomial, okay? And we did that for different dimensions as well. Just as a remark for that was mentioned for related to covariant Lyapunov exponents, what happens with systems with many positive Lyapunov exponents, and there indeed we investigated in a slightly different context. It's not in the Markov chain context, but indeed in that case, we learned that an isotropic proposal is not the most efficient one, and I think this is also related to what you were referring. So what we did is we modified our proposal to be to respect the directions of maximum of positive expansion. So we are closer in the direction of the largest Lyapunov exponent, and not so we squeeze our initial distribution appropriately so that at the time t, in this case when it reaches the exit set, we have something uniform. And so we found that this type of anisotropic proposal is essential in some of these cases. Okay, or it is more efficient than the previous one. Okay, and in the last time, the last minutes I have, I will consider the coupled oscillators case, which probably there are more people in this room that are interested. So if you lost focus and wants to come back in the last 10 minutes, that's a good opportunity to do so. Yes, yes. Okay. Should I sometimes clapping? It wakes up people. Okay, I see. So 5 to 10 minutes about coupled oscillators. Okay. So we'll be investigating here the Hamiltonian mean field model that was discussed before. So there I have an angle and a velocity, and also the Kuramoto model that was also appeared before. I have only the angle. It's an all-to-all coupling of n oscillators, and in the Kuramoto case, the frequencies are quenched and Gaussian distributed. Okay, so the observables I'll be considering will be the finite time largest Lyapunov exponent, as discussed before, and also the order parameter, right? So we can compute the order parameter in these oscillators as summing over all angles of all particles, And if it is not 0, it's indicating some order. So here we will be averaging for every trajectory the order parameter for the first t times. Right? We can drop some transient if we want in the beginning, but it is a time average order parameter for the trajectory up to a given time t, which is what you can do in a numerical simulation anyways. But this time t is then playing the same role as the finite time Lyapunov. And I'm choosing parameters here k or k and m, such that in this case the systems are in the disorder regime. There is no order; it's in equilibrium. Okay, we probably can do also in other cases. So, by the way, this is a work with Shamik Gupta, who some of you know, and was in Dresden in my group, and now is back to India. So first thing we did, now this is the distribution of the largest finite time Lyapunov exponent, finite at the time 10, 128 oscillators. The beta 0 case here, the red symbols here is what we would get through a naive assumption. A standard simulation, what we did, we computed for different betas, and we verified that by drawing different betas, we are biasing our results either to the left tail or to the right tail, right? So we remap to the unbiased case. So we can indeed sample better the left tail if we use a positive beta and the right tail if you use a negative beta. But otherwise, the distributions agree. This is just checking that our algorithm is working. So if we if we join the different betas we have, we can see that we find the distribution with larger accuracy for on the tails, which was our goal. We computed for the Hamiltonian mean field for different sizes n, and we see here that in this regime the system is chaotic, so the distribution becomes narrower and narrower around a given value, which will be the largest Lyapunov exponent of the system, which is positive here. But we are interested in the full distribution here, not only in the largest, in the value it's converging for large n, but for a fixed n, what is the distribution? And because the distribution is getting narrower, it's increasingly difficult to sample the tails. So what we were doing here was to compute the average, the standard deviation, and the skewness, so the first moments of these distributions. So we find that the average is roughly constant, so this is the positive exponent. The width is going to 0, we can see here, but maybe the most interesting observation here is that the skewness is growing. So these distributions converge to a delta, but they converge in a skewed way. Okay? And for these computations, essentially, especially for the skewness, it's important to have a sampling of the tails, because the skewness depends, the higher moments depend more and more on the tails, of course. So we did the same for the order parameter, which in this case is converging to 0. So this is n equals 32, 64, 128. So it is slowly converging to a delta around 0, increasing n now. And again, we find the same picture. The skewness remains positive, or maybe it's even increasing. So it's converging to 0, but it's in a skewed way. And just as an illustration for the Kuramoto, we were also able to do this. In this case, the finite time Lyapunov exponent is going to a very small value, and skewness is also increasing. Okay, and this is the Kuramoto for the order parameter, which is essentially the same, just to illustrate that our method works also for the Kuramoto model. Okay, I had some words about the case of non-hyperbolicities. Why non-hyperbolicities are important. We heard in the last talk by Shmuel Fishman that the issue of stickness to the standard map, which is exactly this setting. So we have this, if we introduce some escape region in the standard map with some KM island here, we get these fat tail distributions. And my view on this is that the existence of an asymptotic universal exponent is still a conjecture. So we would like to be able to efficiently sample these tails. But this is a non-hyperbolic system, and it's more complicated than what I told you before. Essentially, what I can say is that our approach works in correlating the trajectories. We are able to do local steps, but we are not able to do a full metropolis hasting because the acceptance goes to 0. And it goes to 0 because this simplifying assumption doesn't hold. So the probability of going x to x prime is very different from x to x the other way around, and that's why our acceptance is ruined. So we are able to find very rare trajectories, but we are unable to come back. So we are unable to build the proper Markov chain and sample the trajectories. That's the state of the art. It's a work in progress, but I want to take some questions, so I want to conclude now. So let me try to summarize what were my main points. First, I try to convince you that rare trajectories in dynamical systems is an important problem. They matter, and they are hard, a hard computational problem. And then I argue that in order to find an efficient Monte Carlo simulation, we need to be careful about the choice of the proposal. In particular, we need to know information about the dynamical system, right? So about the escape rate, about the Lyapunov exponent, and use the information of the dynamical system into the Markov chain. And this is what is, I think, an interesting problem, because you have essentially two dynamical systems. One is the Monte Carlo, the Markov chain, and the other is the dynamical system you are interested. But essentially, we can only make the Markov chain work if we input information from our dynamical systems, information such as the Lyapunov exponent, or fractal dimensions, or escape rate, right? So, and then we are able to make a successful and efficient Monte Carlo simulation. We have done this for many, we have showed that this works on many cases, but there are many more to do, non-hyperbolicity in our to-do list, but maybe also come closer to some physical problems, climate models, maybe three-body problem, planetary astronomy. Let me finish thanking my co-authors, and especially Georges Leighton, who was my PhD student in Dresden, and also thank you for your attention.